Sometimes the biggest secrets in the universe are hiding in the smallest places. Today, we're diving into one of those secrets, one that was hidden inside a single beam of light. Once scientists figured it out, it completely changed how we see everything, from the tiniest atoms right here on Earth to the fiery surface of distant stars. This is the story of the Zeeman effect. So let's just start with a question that sounds, well, kind of impossible, right? How in the world do we measure an invisible magnetic field on our own sun, which is 93 million miles away? We obviously can't send a probe there. The answer isn't about sending anything to the sun. It's about looking very, very closely at what the sun sends to us. It's light. And this, right here, is the key to the whole thing. The Zeeman effect is, at its heart, a really elegant idea. If you look at the light coming from any element, you see this unique pattern of colored lines, almost like a spectral barcode. But if you put that same element inside a magnetic field, something amazing happens. A single line in that barcode can split into 2 or 3 or even more really distinct, closely spaced lines. That splitting, it's a direct fingerprint of the magnetic field's presence and its strength. But how did anyone even figure this out? Well, the story starts like a lot of great science stories do, with a failed experiment, and then, later on, a persistent scientist who just happened to have a much better tool for the job. You see, the legendary Michael Faraday, he suspected there was some kind of link between light and magnetism, but he just couldn't prove it with the tools he had. Fast forward a few decades to 1896, a Dutch physicist, Peter Zeeman, gets his hands on this brand new, super powerful diffraction grating. Think of it like a super prism that could spread light out with incredible detail. He decides to redo Faraday's old experiment, and this time, boom, he saw it. The spectral lines from a flame literally broadened and then split apart when he switched on a powerful magnet. Just a few years later, he and Hendrik Lorentz explained the physics behind it, and they shared the Nobel Prize for their work.
But of course, science is never quite that tidy. While some elements split exactly the way Lorentz's classical theory said they should, that's what we now call the normal Zeeman effect, a whole lot of other elements didn't. They split into these wild, complex patterns that seem to follow no rules at all. This became known as the anomalous Zeeman effect, and frankly, it was a massive headache for the entire physics community.
And this quote just perfectly captures what a huge problem this was. That's from Wolfgang Pauli, one of the most brilliant physicists of the 20th century. You see, the solution to this anomalous puzzle wasn't going to be found in the old physics. It would require a total revolution in our understanding of the universe, the birth of quantum mechanics, and the discovery of a truly bizarre property of the electron called spin.
Okay, so that brings us to how we understand it today. What is actually happening inside that atom when we turn on the magnet?
So try to picture an atom's energy levels like the rungs on a ladder. Normally, an electron can jump from a higher rung to a lower one, and when it does, it releases a single specific packet of light. That's our spectral line. But when you apply a magnetic field, it's like each rung on that ladder splits into several smaller subrungs, all very close together. This means the electron suddenly has new places it can jump to, and each one of these new possible jumps releases a slightly different color of light. And that's the splitting that we see. Now here's where it gets really interesting. The strength of the magnet completely changes the game. In a pretty weak field, the electron's own orbital motion and its quantum spin are kind of linked up, and that's what creates those complicated anomalous patterns. But if you crank that magnet way, way up, the external field becomes so strong that it just overpowers the atom's internal forces. And what happens is that this intense interaction actually simplifies the splitting, forcing that complex pattern back into a much cleaner, predictable set of 3 lines. This might all sound like a pretty obscure thing you'd only see in a physics lab, but trust me, understanding it has unlocked an absolutely staggering range of technologies and entire fields of science. This is where the story really pays off. Let's circle all the way back to that first question about the sun. In 1908, an astronomer named George Ellery Hale pointed his telescope at a sunspot, carefully analyzed its light, and saw that telltale splitting of the spectral lines. It was the first definitive proof that magnetic fields existed anywhere outside of Earth. The Zeeman effect had just gone from being a lab curiosity to an absolutely essential tool for astrophysics. And its impact today is just incredible. We use it to map the magnetic fields of stars across the galaxy. It's fundamental to laser cooling techniques that chill atoms down to near absolute zero. A related effect on the atom's nucleus is literally the principle behind every single MRI machine in every hospital. It's used in fine-tuning atomic clocks, in developing quantum computers, and get this, It might even be the mechanism that allows birds to see the Earth's magnetic field and navigate during migration.
So, from a mysterious little split in a line of color to a foundational tool of modern science, the Zeeman effect is just this perfect reminder that sometimes the absolute biggest discoveries are waiting for us in the tiniest details. It really makes you wonder, what other secrets are still out there hiding in plain sight inside just a single beam of light?